Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be looking at the birthday problem. The birthday problem is not really directly related to anything we've done so far, but it's a classic example in basic probability. You should know it as a student, and I would be terribly remiss as your instructor if I didn't go through it with you. So, here's the question we want to answer. What's the probability that at least two people in a group of N have the same birthday? Alright, that's the question we want to answer. What's the probability that at least two people in a group of N have the same birthday? I've got to make some assumptions in order to tackle this problem. First assumption I'm going to make is that I have a 365-day year. We're not going to account for leap years and leap days and things like that. Two, we're going to assume that all days are equally likely to be born on. I'm sure the Census Bureau may have better data than that, and probably there are some days that are more likely than others for births, but we're going to assume that every day of the year is equally likely to be born on. Third thing is we're going to assume that we have no twins or triplets or higher order multiples. No quadruplets, quintuplets, etc., etc., etc. All right? Okay. And we're going to solve the problem somewhat in reverse. The probability that at least two people have the same birthday equals 1 minus the probability that no two people have the same birthday. So it's actually the probability that no two people have the same birthday that we're going to solve first, and then we'll eventually subtract that from 1 and answer the question we're after. Okay? All right. Let's piece this together. First thing, the total number of ways that N people can have birthdays total number of ways that N people can have birthdays is 365 raised to the nth power. We're assuming that all birthdays are independent. And the result here, 365 raised to the n, includes all of those cases when the group of n people do have coincident birthdays and when they do not have birthdays. So coincident birthdays are irrelevant. Okay, this is just simply the total number of ways that a group of n people can have birthdays. 365 raised to the n. Everybody's got an independent birthday. Common birthdays are allowed, and they may or may not, the group of n people may or may not have common birthdays. That's irrelevant at this point. All right. Next thing, more interesting, is the number of ways n people that n people can have birthdays with no coincidences is, let me write this down and then I will dissect it for you. We're going to call this a capital N. 365 times 364 times 363 times all the way out to 365 minus n minus 1. And so what does this mean? The first person that we go up and talk to and ask them what their birthday, they can be born on any of the 365 days. So first person can be born on any day of the year. For no coincidences, that means that the second person has 364 days they can be born on. And the third person can be born on 363 days. And so on and so on. Okay? Capital N tells me the total number of ways that n people, little n people, can have birthdays when there are no coincidences. Written in factorial shorthand notation, capital N, it can be written this way: 365 factorial divided by 365 minus n factorial. All right. So, the probability of having no common birthdays of having no common birthdays is n divided by 365 raised to the little n power. So the numerator is the number of ways that we can have birthdays when there are no coincidences. The denominator is the total number of ways that little n number of people can have birthdays, regardless of whether or not there are coincidences. Plugging in capital N from the previous page, we have 365 factorial divided by 365 minus n factorial times 365 raised to the nth power. Okay? And then one last step to get to the question we asked early on was the probability of at least 2 people So the probability of at least 2 people out of a group of n having the same birthday is capital P. It's going to be 1 minus capital N divided by 365 raised to the nth power. And that is 1 minus 365 factorial divided by 365 minus n factorial times 365 raised to the nth power. Okay? That is our result. So for example, if we plug in n equals 20 people in a room together, we find that the probability that at least 2 of them have the same birthday is 41.14%. If I put 25 people in the room, the probability of at least 2 of them having the same birthday is up to 56.87%. And as we'll see in a second, if n equals 50, the probability of at least 2 people having the same birthday it's going to be greater than 95%. All right. So what I did was I wrote a short program in MATLAB to evaluate that relationship, and this was my result. In the denominator, we have the number of people in the room. This is little n, and there's an error in the title of this figure. This is the probability of at least 2 people in the room having the same birthday. Okay, it's not necessarily the probability of exactly 2 people. We can have more than 2 people if we want. This is the probability of at least 2 people having the same birthday. So if we look here at n equals 50, we can see that the probability is pretty high that at least 2 people will have the same birthday. Looks to me like it's about 96–97%. And moreover, if we get a room with 60 to 70 people in there at the same time, the probability approaches very nearly 100% that at least 2 people will have the same birthday. All right, well, that's it. That's all I have for you today. If you have any questions, as usual, please just let me know, and I will answer them as quickly and fully as I am able. Have a nice day. Bye-bye.